There are several applications of union find operation in algorithms. In this video, we will look at how union find operation can be used to find number of connected components in a graph. Let us consider a graph G. This graph has 7 vertices, and by looking at the graph, we can say that there are 2 components. It is easy to see here that there are 2 connected components. The application of union find operations becomes more relevant when we deal with large graphs. So let us look at how union find operation can be applied to find the same. Initially, we have an empty set. Now, since we have 7 vertices, so we will create 7 disjoint sets, each containing one vertex. We will also have a parent array P where all the elements are initialized to -1. Then we will perform union operation on sets if there is an edge between the vertices and the vertices are not in the same set. So we have an edge between vertex 1 and vertex 2. Now we need to find whether vertex 1 and vertex 2 are in different sets. Vertex 1 belongs to set 1 and vertex 2 belongs to set 2. So they are in different sets. Therefore, we will perform union of set 1 and set 2. So now after the union operation, both the vertices 1 and 2 will be in the same set. Then we have an edge between vertex 1 and vertex 4. Vertex 1 belongs to set which contains 1 and 2, and vertex 4 belongs to set 4. So they are in different sets. Therefore, we will perform union of set which contains 1 and 2 and set 4. So now after the union operation, vertices 1, 2 and 4 will be in the same set. Then we have an edge between vertex 2 and vertex 3. Now we need to find whether vertex 2 and vertex 3 are in different sets. Vertex 2 belongs to set which contains 1, 2 and 4. And vertex 3 belongs to set 3. So they are in different sets. Therefore, we will perform union of set which contains 1, 2 and 4 and set 3. So now after the union operation, vertices 1, 2, 4 and 3 will be in the same set. Then we have an edge between vertex 2 and vertex 4. Vertex 2 and vertex 4 belongs to the same set. Therefore, we do not perform the union operation. Then we have an edge between vertex 3 and vertex 4. Now we need to find whether vertex 3 and vertex 4 are in different sets. Vertex 3 and vertex 4 belongs to the same set. Therefore, we do not perform the union operation. Then we have an edge between vertex 5 and vertex 6. Vertex 5 belongs to set 5 and vertex 6 belongs to set 6. So they are in different sets. Therefore, we will perform union of set 5 and set 6. So now after the union operation, vertex 5 and 6 will be in the same set. Then we have an edge between vertex 5 and vertex 7. Vertex 5 belongs to set which contains 5 and 6, and vertex 7 belongs to the set 7. So they are in different sets. Therefore, we will perform union of set which contains 5 and 6 and set 7. So now, after the union operation, vertices 5, 6 and 7 will be in the same set. Then we have an edge between vertex 6 and vertex 7. Now, we need to find whether vertex 6 and vertex 7 are in different sets. Vertex 6 and vertex 7 belongs to the same set. Therefore, we do not perform the union operation. Now, we have examined all the edges of the graph and placed vertices in disjoint sets based on the edges between them. You can observe that after considering all the edges of the graph, we have 2 disjoint sets. This means that we have 2 components in the graph. So this is how we can use union and find operations to create disjoint sets and to know how many components are there in the graph based on the number of disjoint sets remaining. Now let us look at the algorithm. We will call this algorithm as connectedComponents, and this algorithm takes the graph G as the parameter. Then within the algorithm, we will have a for loop for each vertex V that belongs to the graph. And within this for loop, we will create disjoint sets for each vertex using the statement makeSet, and pass the vertex v. Then we need to consider each edge. So we will have for each edge u and v which belongs to graph G. Now within this for loop, we will check if the vertex u and vertex v belongs to different sets. So we will have the if statement with the condition find operation of u not equal to find operation of v. If this is true, that means vertex u and vertex v belongs to different disjoint sets, and we will perform union operation by calling union and passing vertex u and vertex v. So this is the algorithm for computing the connected components. Now let us look at the time complexity of this algorithm. The first for loop of this algorithm creates v number of disjoint sets. So if there are n number of vertices in the graph, then this for loop will execute for n times. Then the second for loop executes depending on the number of edges in the graph. So if there are n number of edges, then this for loop will execute for n times. Then this for loop makes calls to find algorithm, and find algorithm takes O of n as the time complexity. And within the if statement, we have a call to the union algorithm, which takes constant time. Therefore, the second for loop takes at most O of n square. So we can say that the overall time complexity of this algorithm is O of n square. So this algorithm will create disjoint sets, and at the end, we will be able to know how many components are there in the graph based on the number of disjoint sets remaining.